Whether you're cramming for a system design interview or you just want to understand the magic behind the apps you use every day, there's one tool that just keeps popping up: Redis. It's famous for being the Swiss Army knife of databases, and today we're going to find out exactly why. We're going to break down what it is, how you scale it, and how it's used to solve some of the biggest problems in software engineering. All right, here's our game plan for today. We're going to kick things off with why Redis is such a big deal. Then we'll pop the hood and look at its core design. After that, we get practical. We'll talk about scaling, caching, and rate limiting. And finally, we'll dive into some of its most powerful features that unlock some seriously cool capabilities. So first things first, why even bother with Redis? Well, the simple answer is that it's one of the most versatile tools you can have in your engineering toolbox. You can really think of it as the ultimate utility player on a championship team. And that kind of makes you wonder, right? How can one piece of software do so many different jobs? I mean, how can it be a cache, a message queue, and a database all rolled into one? Well, that versatility is exactly what makes it so incredibly powerful. Look, we're not just talking about a simple key value store here. We're talking about building blazing fast caches, for sure, but also things like distributed locks to stop data corruption, real-time leaderboards for games, background job queues, and critical pieces of infrastructure like rate limiters. The list just goes on. This is what people mean when they say bang for your buck. You learn this one tool and suddenly you know how to solve dozens of common system design problems. And here's the real kicker. For all that power, Redis is surprisingly simple to wrap your head around. Its mental model is just so clean. Unlike a big, complex SQL database where figuring out a slow query can feel like some kind of dark art, with Redis, you can actually reason about what's happening. And that simplicity is a massive advantage, especially when you have to explain your design choices in an interview. Okay, so let's pop the hood and see how this thing actually works. To really get Redis, you've got to understand 3 core ideas that define pretty much everything about it. This sentence right here, this is the key to the whole kingdom. Every single word in this phrase is critical. Single-threaded, in-memory, and data structure server. Each one of these design choices has massive consequences for performance and how you're supposed to use it. Let's break them down. First up, single-threaded. Now, in a world of multi-core CPUs, that sounds like a bad thing. And in a way it is. One Redis instance can't use all your computer's cores. But the trade-off is absolutely worth it. You get simplicity and predictability. Commands run one at a time, first in, first out. This means every operation is automatically atomic, and you get to completely sidestep the nightmare of locks and weird concurrency bugs that plague multi-threaded systems. Next up, in-memory. This is where that legendary speed comes from. All your data lives in RAM, not on some slow spinning disk. This allows for response times in sub-milliseconds. The trade-off? Well, by default, your data isn't durable. If the server crashes, poof, the data is gone. This completely changes how you think about using it. Instead of batching up requests like you would with a SQL database, you could just fire off thousands of tiny individual requests per second, and Redis will handle them, no problem. And finally, data structure server. This right here is where Redis really shines. It's not just storing plain old strings. The values themselves can be these complex data structures, lists, hashes, sorted sets, the very same ones you learned about in your algorithms class. Redis gives you these powerful building blocks and lets you use them in a distributed, high-performance way. You can apply what you know about data structures directly at the architecture level. It's awesome. Okay, so that brings up a really obvious question, right? If Redis is single-threaded, how on earth does it handle the massive scale of today's applications? The answer is simple. You don't scale up, you scale out. You go from one Redis server to a whole cluster of them working together. Now, scaling Redis usually happens in stages. You could start with a single node, but honestly, that's a super fragile setup. The first real step is replication. You have one primary node that handles all the writes, and it streams its changes to a bunch of replica nodes. This is great for scaling your reads and for making your system more available. But to scale writes, which is the real bottleneck, you need the final step, clustering. This is where you actually split or shard your data across multiple primary nodes. So how does this even work? How does your app know which of the many nodes to talk to? Well, the process is surprisingly simple, and it all happens on the client side. The client takes your key, runs a hash on it, and that hash maps to one of about 16,000 slots. The client keeps a little map of which node owns which range of slots, and it sends the request directly to the correct node. There's no central router slowing things down, which makes it incredibly fast. And this brings us to what is probably the single most important concept for scaling Redis. Since the data is spread out based on a hash of the key, the way you name your keys is what directly controls how your data is distributed. Your key design is your sharding strategy. You, the developer, are in complete control of the whole thing. Of course, this leads directly to a classic system design failure, the hotkey problem. Imagine one specific key gets a massive amount of traffic, like the cache for a viral video. It doesn't matter if you have 100 nodes in your cluster. All that traffic is going to hammer the one single node that owns that key's slot, totally overwhelming it while all the other nodes just sit there doing nothing. So your scaling strategy has to plan for this by designing keys that spread the load out nice and evenly. Okay, that's enough theory for now. Let's get practical and look at how Redis is actually used in the real world. We'll start with its two most popular jobs, high-speed caching and rate limiting. The most common caching pattern you'll see is called cache aside. Here's the flow. Your application first checks Redis to see if it has the data. If it does, that's a cache hit. Great, you just return it right away. If it's not there, a cache miss, your app has to go to the slower primary database to get the data. But, and this is the important part, before it sends the data back, the app writes that result into the Redis cache. That way, the very next request for that data will be a fast cache hit. This simple pattern is incredibly good at protecting your main database from getting overloaded. But a cache is only good if you have a way to clear out old data. Redis gives you two main ways to do this. The first is setting an explicit time to live, or TTL. You basically tell Redis, hey, this key should only exist for 60 seconds. It's predictable, and it's perfect for data that you know will go stale. The second way is eviction. You just let the cache fill up, and when Redis runs out of memory, it automatically starts kicking out the least recently used IDAs to make space. It's a bit less predictable, but it can be super efficient, and it's how other popular tools like Memcached work. Now, this is where things get really clever. Thanks to its atomic NCR command, building a distributed rate limiter in Redis is almost trivial. For every user request you want to limit, you just increment a counter key. If that counter goes above your limit, you reject the request. Simple. And if it's the first request in a new time window, you also set an expiration on the key. Once that key expires, the counter vanishes, and the user's limit is reset. It's such an elegant and powerful pattern, all with just two basic commands. So far, we've pretty much just talked about simple key value patterns. But the real power of Redis, the stuff that makes it so special, is in its advanced data structures. Let's look at two of the most important ones, streams and sorted sets. So a Redis stream is basically a distributed append-only log. If you've ever worked with something like Apache Kafka, it's a very similar idea, but it's built right into Redis. You can add new entries to the end of the stream, and each one gets its own unique time-ordered ID. This makes it the absolute perfect tool for building a reliable background job queue. Here's how that job queue works. First, jobs get added to the stream. A consumer group acts like a bookmark, keeping track of which jobs have been processed. You can have multiple workers that ask the group for new jobs. A worker then claims a job so nobody else can pick it up. Now, if that worker crashes halfway through, the job can be reclaimed by the group and given to another worker. The key takeaway here is this system gives you an at least once delivery guarantee. This means in a failure, a job might get processed more than once, but it will never get lost. Now let's talk about sorted sets. These are perfect for things like real-time leaderboards. Imagine you want a list of the most liked tweets about tigers. The tweet's ID would be the member, and the number of likes is the score. With one simple command, zadd, you can add a new tweet to the leaderboard or update the score of one that's already there. And check this out. Updating tweet_ID_1 from 500 to 501 likes uses the exact same command. It just overwrites the score. So simple. But what about performance? Adding an item to a sorted set takes logarithmic time, which basically means as your leaderboard grows to millions of tweets, each update gets a tiny, tiny bit slower. So here's the pro trick. You keep the set small. You can periodically run a command to just trim the leaderboard, keeping only, say, the top 1,000 tweets. This makes sure your leaderboard stays lightning fast, no matter how much traffic you throw at it. All right, let's wrap up with two more specialized tools that solve really complex problems with just a few simple commands: geospatial indexes and publish-subscribe messaging, or pub/sub. The geospatial index is a perfect example of how clever Redis's design is. Under the hood, it's actually just a sorted set. It uses a really cool technique called geohashing to turn a latitude and longitude into a single number, which then becomes the score. This brilliant little trick allows Redis to run incredibly fast searches, like find me all the bike stations within a 5-kilometer radius. And the commands themselves are so intuitive. You just use geoadd to add a location to your index along with its coordinates, and then you use geosearch to find everything within a certain radius of another point. It's just a really elegant solution to a very common problem. Now for a totally different kind of problem, how do all the different servers in your system talk to each other? Think about a chat app. User A is connected to server 1. They send a message to user B, but user B is connected to server 5. How does server 1 know where server 5 is? This is the exact problem that the publish-subscribe pattern is designed to solve. The solution is to use Redis as a central message broker. Your servers can subscribe to named channels. So in our chat app, server 5 would subscribe to a channel called user B messages. When server 1 wants to send a message to user B, it just publishes that message to the channel. Redis then immediately routes the message to any server that's subscribed, in this case, server 5. The servers themselves never have to know about each other's existence. But, and this is a huge but, there's a big catch with PubSub. It provides what's called at-most once delivery. This is a total fire and forget system. If a subscribing server is offline for even a split second when a message is published, that message is gone forever. It's extremely fast, but it is not reliable. If you absolutely need a guarantee that your messages will be delivered, you have to use a more robust system, like the Redis streams we talked about earlier. So, let's quickly recap the most important points. 1. Always remember the core identity of Redis. It's a simple, versatile, in-memory data structure server. 2. Its real power is unlocked by those specialized data structures, which let you build really complex features like job queues and leaderboards. 3. Scaling Redis is all about scaling rights, which means you have to be smart about your key design to avoid hotspots. And 4. All these building blocks allow you to implement many of the most important patterns in modern systems. And I'll leave you with one final question to chew on. We've spent this whole time talking about how the simplicity of Redis is its greatest strength. But when could that simplicity flip and become its greatest weakness? In what kind of scenario would its single-threaded design or its lack of guaranteed durability become a total deal-breaker? Answering that question is the next step to truly mastering this incredible tool. Thanks for joining me.
ご覧いただきありがとうございます。